Today we'll be discussing the unit impulse function. This function was first introduced by Paul Dirac, an English theoretical physicist, who was the first to formulate quantum electrodynamics. Dirac was the Lucasian professor at Cambridge, which is the same chair that was held by Newton and Stephen Hawking. He predicted the existence of antimatter, and won a Nobel Prize for his contributions to physics. What is the unit impulse function that Dirac introduced? First, we give it the symbol delta of t, and you should know that it's also called the Dirac delta function. And here's its definition. The Dirac delta function is equal to 0 for all time not equal to 0. And you see the for all time symbol that we introduced before. Now, if the signal is 0 for all time not equal to 0, it doesn't seem like it could be very useful. But the key attribute of the Dirac delta function is that the integral from minus infinity to infinity of the Dirac delta function is 1. That it has a unit area under the curve. So it's 0 everywhere, but right in the region of 0, or precisely at 0, it actually has some area under the curve. We can visualize this as an infinitely tall, infinitely thin pulse that occurs at time 0. And so you see here is how we draw it on a graph of the signal. One way of generating a Dirac delta function is through a limiting process. We'll have a pulse of unit area. It will extend from minus epsilon over 2 to epsilon over 2, and the height will be 1 over epsilon, so that the area underneath will be 1. Then we take a limit of this pulse as epsilon goes to 0. The area stays constant and is 1, but it becomes infinitely thin. This is a way we can think about the Dirac delta function. Now, the Dirac delta function may seem like a rather strange thing to be introducing, as obviously no physical signal can be an impulse. But it turns out the Dirac delta function is going to be very important to all the things that we do in this class. And you'll begin to see why as we start talking about Laplace transform and convolution. Now, if we take a Dirac delta function and we multiply it by a constant, we'll get another impulse. But this impulse will have a different area, or as we refer to it as strength. The strength will be multiplied from 1 for the Dirac delta function to the constant that we multiply it by, in this case k. We can see that the strength of the signal k delta of t is k by performing the integral. We integrate from minus infinity to infinity of the signal k delta of t. The k can be pulled out of the integration, and then we just have the integration from minus infinity to infinity of the Dirac delta, which of course is 1. Let's look at multiplying a continuous function by an impulse and see what happens. So our function that we're going to multiply by the impulse we'll call phi of t, and we multiply it by delta of t. Now, we should point out what we're going to do is multiply the values of phi by the values of delta at each and every time to make a new signal. And let's talk about the properties of that signal. Well, clearly, because delta of t is 0 everywhere except t equals 0, then phi of t times delta of t will be equal to 0 at all times except time 0. And then if we perform the integration from minus infinity to infinity of phi of t times delta of t, we're going to get phi at time 0. Simply because the only value of phi that matters is the value at 0, all the other values are lost because they're being multiplied by 0 in the Dirac delta function. So what we do is we just pick off the value of phi at the time 0 when we perform this integration. Now let's consider the signal phi of 0 times delta of t. It satisfies the exact same conditions as phi of t times delta of t. It's 0 at all times except for time 0, and the integral from minus infinity to infinity of phi of 0 delta t is phi of 0, because phi of 0 is just a constant. So we see that the signal phi of t times delta of t and phi of 0 times delta of t are in fact the same signal. This property of the Dirac delta function is referred to as the sampling property. Again, integral from minus infinity to infinity of phi of t times delta of t will be phi at time 0. Or more generally, if we're dealing with a delayed Dirac delta function, delta of t minus cap t, where cap t is the delay, and we perform the integral from minus infinity to infinity of phi of t times this delayed Dirac delta function, we'll find out that integral gives the value of phi at the time of the delay, cap t. On the next 2 pages, I will be doing some complicated calculus in order to show you an important property of the unit step function as it relates to the Dirac delta function. So, to start with, let's consider the integral from minus infinity to infinity of u of t times d phi dt. Now, phi here is just some arbitrary function, not terribly important to what we're going to analyze. And u of t is the unit step function. Recall the unit step function is 0 for time less than 0, and it's 1 for time greater than 0. So this integral from minus infinity to infinity of u of t times d phi dt can be written as the integral from 0 to infinity of u of t times d phi dt. Because before time 0, u of t is 0, so there's no contribution from that integral. Now that integral must be equal to the difference between phi at time infinity and phi at time 0, simply because we're just integrating d phi dt, and of course the integral of d phi dt is phi. So we know what this integral equals. Now we're going to actually perform the integration by doing integration by parts. So we'll integrate minus infinity to infinity of u of t times d phi dt. And of course when we integrate by parts, that will be u of t times phi of t evaluated at the 2 limits of integration, minus the integral from minus infinity to infinity of du dt times phi of t dt. So this is just classic integration by parts, where one part of the integration is played by u and the other part is played by phi. Let's start by examining the first of these 2 terms, the u of t times phi of t, which we have to evaluate at plus infinity and minus infinity. Well, u of t times phi of t at minus infinity will be 0, since u at time minus infinity is 0. So we know this first term will evaluate out to phi at infinity. And we know the integral evaluates to phi at infinity minus phi of 0, and also evaluates to phi at infinity minus the integral from minus infinity to infinity of du dt times phi. So working with this equation, we can see that phi at time 0 must be equal to the integral from minus infinity to infinity of du dt times phi of t dt. What this is showing is that du dt has the same sampling property as the Dirac delta function. That shows a rather suspicious connection between the Dirac delta function and the derivative of the unit step signal. Are these the same signal? The Dirac delta function has 2 properties. One is the sampling property, and the other is that it is 0 at all times except for time 0. So what about du dt? Well, du dt obeys the sampling property, as we saw on the previous page. And if we look at du dt, we'll find it 0 for all time not equal to 0. After all, if we look at the step function u, clearly its slope is 0 at all times except right at time 0. So we see du dt has exactly the same properties as the Dirac delta function, and therefore they must be the same function. So the time derivative of a step function is the impulse function. This is an important property which we'll use throughout the class. So since the derivative of a unit step function is a Dirac delta function, we also know that the integral of a Dirac delta signal is a unit step signal. So we write u of t is the integral from minus infinity to t of delta of tau d tau, where tau is the dummy variable of integration. So when we integrate an impulse function, we'll get the unit step signal. What if we integrate the unit step signal? Well, it's easy to show that the integral of the unit step signal is the ramp signal that we learned about before. So now we have a connection between 3 signals that we've seen so far in this class: the Dirac delta signal, the unit step signal, and the ramp signal. And the relationship between the 3 is one of integration.